to Germany and Serbia.
As long as it's always SwedAPL, I'm okay.
That would be great. Yeah, so thanks for giving me the first slot, so I can relax a bit. I'll be on again at the end, but now I have time to prepare that as well. So I'm going to try and sort of set the stage and talk a bit about what concurrency is, the different kinds of concurrency, and in particular what Dyalog is trying to do to respond to your need for speed, which is growing all the time. Hopefully I won't say too many obvious things. I guess this is fairly obvious. You know, the data that you have is growing. In fact, the rate of growth of data is growing. And the sophistication that is demanded of your analysis of this data, or at least your ability to simulate things and get these Monte Carlo simulations to converge. How many people here need converging Monte Carlo simulations? Oh, I've come to the wrong place. No, there were a couple. So you need to do more and more analysis on bigger and bigger data. And this was all great until about 10 years ago. We didn't have to do anything because the clock frequencies just doubled every 18 months, and we were able to stay on top of things without actually doing anything, because there was this guy, Gary Moore. Well, I suppose it's not because he invented the law that this actually happened, but all the way back in 1965, one of the founders of Intel discovered that the number of transistors per square inch that Intel was putting onto the chips was doubling roughly every year. And he predicted that that was going to continue for the foreseeable future. And it more or less has. It slowed down a bit. It's every 18 months. The data density on the chips has been doubling. And that part of it could still continue. The thing that we were all taking advantage of was something I did research, Wikipedia, into this. There was a guy called Dennard who defined this thing called Dennard scaling, which is like a special case of Moore's law, where he says that on microprocessors you'll be able to scale all the oxide thickness, the length of a transistor, and so on by a scalar, by a constant factor. And what was good was that the power consumption of a chip is proportional to the size. So as the size of the transistors went down, the power that they consumed was going down. And that meant that we could increase the clock speed because the power consumption is related to the number of state changes you need. These chips burn electricity when they change state. So for decades, because the chip size was going down, we could increase the clock frequency and the chips wouldn't increase massively the power consumption. So that's why it went on and on and on. But in the mid-2000s, apparently at 90 nanometers, at least the technology they were using then, the gates became so thin that even when they were not switching, they started leaking large quantities of current. And that meant that they couldn't get any smaller, around 2005. And then apparently they had new technologies, purer silicon and different types of oxides and so on. And I think now the latest chips are at 20 nanometers. I don't know, Klaus, you're in it. Is that right? About 20 nanometers? Even less, okay. So they can go down, you know, they've been able to scale it a little bit more, but you can see that the numbers I found from 2007 to 2011, the clock speeds went up by 33%, whereas from 94 to 98, they went up by 300%. So it's still going up a little bit, but not the way it used to. And there's this wonderful graph that only goes up to, well, it goes past this point anyway, and it shows that the number of transistors that they can put on an integrated circuit, well, that's doing just fine. That's just going up and up and up. But around this point here, the clock speed went up to here, and then it just, so this is a logarithmic scale, right? So a straight line here is essentially doubling at a certain frequency. So the clock speeds tapered off. The power, when you got to about 100 watts, you also have this problem that when you have a chip this size and you're consuming 100 watts in a 1 by 1 millimeter square, things start to get really hot. And they try to go 3D and they do various things, but You can't really reasonably go above that. And the slides will be available. There are links if you want to do more research into this. So the solution to this, since we need more speed, we have more data, is to go parallel. Instead of putting more and more transistors into each CPU, you simply have to make more of them, cut the chart off before the power consumption goes completely crazy, and then have several of them. And there's sort of two fundamentally different approaches that are being followed by the hardware manufacturers at the moment. You have the thing called a GPU or a GPU, where the GP stands, the first GP is for graphical processing unit, and the GP stands for general purpose, I think. So general purpose because NVIDIA and the other people who make these things discovered that there was a market for using this technology to do computation. So you get GPUs. And this is a thing which should be very dear to us APLers because it's a single instruction, multiple data architecture. You have 100 cores or 250 CUDA cores. CUDA is a version of C that you use to program these things. And you essentially have to give all 250 cores, you can cut them up into blocks and so on. But essentially you're giving each one this, is executing the same instruction, looking at different pieces of data. So this is a very parallel but single instruction multiple data machine. So if you have data parallel applications, and we'll talk about that in a minute, where you're doing the same thing, same instruction on lots of data, that fits nicely into a GPU. And then Intel is going a different direction with this architecture that they call Knight's Landing and Knight's Hill and Knight's Mountain and stuff like that. Where what they've done is they've rolled time back and they've taken Pentium cores from around that can run at about 1 gigahertz, so a simpler CPU than the latest architectures. And they're doing lots of work on making them more power efficient and being able to turn them on and off as you need them and so on. And they make these boards where you have growing numbers of full Intel instruction set machines. So they run legacy Intel code on these different CPUs. And at the moment, this technology is still significantly more expensive. It's still in its infancy. But in 5 years' time, who knows, these may become roughly equivalent in price. So here's a picture from Intel. So they've got over 60 cores. They are out of order, and I suppose that's a good thing. And they're working on lower power consumption and then sharing data between all of these guys. Okay, so then you may need, of course you can buy lots of boxes and put them together in a network. Buy them, ask your IT department, or we actually have customers now we're working with who are planning to use this in the next year or two. So if you think it's interesting, talk to us. We're developing tools for that. This is Amazon's EC2 Elastic Compute Cloud pricing, where you can, the smallest Nano Linux, no, this is Windows, you can rent a CPU with 0.5 gig of memory with block storage only for less than 1 cent per hour. If you just want to do something really simple, like run a web server or something, you might go there. And then for us, you can also buy, virtual machines with GPU. So Amazon will rent you a machine with lots of memory, lots of parallel cores. They'll guarantee that you have access to an SSD and so on. And then you get up to like paying $3 an hour for the machine. So you need to have something really useful to do. But you can buy these things and you can scale, or we're trying to help you be able to scale. So these fundamental types of concurrency that we talked about. Data parallelism, I have an APL expression, so A to the power B plus dot times C, so you've got some very large arrays, and you're doing the same instructions. Okay, this one here is a combination of instructions, but essentially the interpreter or a compiler can look at that and it can know exactly how the data is going to flow. And it could then map it to a GPU reasonably effectively. So you can analyze the data flows, and then you can do what Bernanke will call, I don't know, I have to be careful when I refer to Bernanke because he's very precise with terminology. I'm probably using this word incorrectly, but you take these loops, there are 2 loops there, or actually there's 3 or 4 loops there. You find a way to turn them into one loop so that you maximize the use of cache, and you can make that run fast. And then you have task parallelism. So my example APL expression there is an array of 2 namespaces where you call the foo function inside each namespace. That might be the same function. It might be 2 completely different functions. You pass an array in. So you have several not necessarily identical things that you need to do. And they might also not necessarily start and finish at the same time. In this expression here, you force them to start and finish at the same time, but you might want to launch one and then launch another one. And there the trick is to distribute the data efficiently, collect it. And because of this business of starting and stopping, you want some logic to try and keep as many processes busy as possible. And if you have this result feeding into another result, try and optimize the pipeline so that you don't have to wait for the whole thing and get idle time. So, I mean, fundamentally in concurrency, the task is moving data. The difficult thing is moving data around, distributing it to the processes that need to work on it, and then synchronizing. And in addition to that problem of the clock speeds stopped flattening out about 10 years ago, in that period of time where the CPU clock speeds were increasing nicely, the memory bandwidth and the memory fetch speed did not increase at the same time. So when I started playing with computers, if you had to load data from memory, it was like maybe 1 or 2 wait states. The CPU had to wait a clock cycle while the data was loaded from memory. Now, the CPUs have larger and larger cache, and level 1 cache and level 2 cache, and level 3 cache, which gets slower and slower and is shared by more and more components. So you've got cache, which is just shared by 1 core. You've got cache, which is shared by all the cores on the chip. And then you might have these Knights Landing fast memory pool shared by all those machines. But if you have to go to real memory today, you have to think of it the way we used to think of hard disks back when I started computing. Having to leave cache and go and load data from RAM is something like 100 wait states. The CPU is going around 100 clock cycles doing nothing until the next cache line is filled. And if you have to transfer it to another virtual machine or a GPU, it gets even slower. And I think what we're finding is that finding like one general solution. Well, we have APL, it's an array notation. All the clever people at Dyalog and should sit down with Bernanke and our own zoo, and they should just work out how to compile it, and it should just use all the cores. Well, it can't be done. Finding general solutions is very hard. You need to provide a variety of different models for the different types of concurrency. And I think certainly at the moment you need to allow the user to help specify where the parallelism is. So here are some things that we are doing that I felt were somehow related to at least the need for speed and to a very large extent also concurrency. I'm not going to read them up because I'll go through them all, and we're running a bit late. I'll go to the next slide where I've turned green the ones which I think are directly related to concurrency. So you can say the bytecode execution engine and tuning the interpreter, is that not related to concurrency? Well, I suppose it is in the long term because it helps, speed always helps, and then there are ways to insert concurrency into those activities as well.
Sorry?
Ooh. Don't be sorry.
In a wrong place. Sorry.
Thank you.
Enjoy.
So sort of at a very fundamental level, we have this 30-year-old interpreter full of optimizations to make it run fast on 16-bit Linux in 1986. And we now have enough people that we're sort of really systematically going through optimizing for the architectures of today. In version 15.0, which will be released in a couple of months, the really big performance improvement we've done is something you might say, we almost got this for free. We upgraded 10 years worth of Visual Studio C compiler and about 5 years worth of GNU CC. On AIX, we've always been keeping it more or less current. But it wasn't that easy. We switched compilers, some things, a lot of things, nearly everything got faster, some things got slower. We had to do a fair amount of work to rewrite algorithms that the new compiler didn't like. But today, I'm really happy. This is the first release where we've had one of these performance. So this is our performance QA. We test 14,000 expressions, divide them up into groups. This is a comparison of 15.0 and 14.1, and it's entirely blue. There isn't a single piece of red. Yeah, well, J-code, Roger Huey did most of the work on that. On Linux, most of our focus is still on Windows in terms of performance, because that's where the paying customers are, though that's changing. So this is the same chart for Linux, where we also only moved 5 years forward. And here's a chart just going back as far as I could easily go, back to 13.2, where you can see that it's sort of, the graph is up here somewhere for 3 releases. I couldn't go back to 12.1 or it would have, and notice it's a cut off here. This actually goes like that. So that's going really well. So for version 16, send us your benchmarks, please, if you haven't done so already. We will have 1 or 2 people every single release working very hard on rewriting the old algorithms. We've got one really good thing that Scholes has promised to do before he retires. And the great thing about this is it's really a catch-all, because then it doesn't matter how long it takes to compute anything. Okay. No, but Scholes says it doesn't really matter if he does this before he retires or not. He's pointed out, even if he doesn't make it before he retires, it's never too late. Okay, then we have this project that that Aaron has, Aaron Zhu, you've probably seen him if you come to our user meetings. He's working on. This is a real compiler. It's not in 100% compatible with Dyalog APL. You have to limit yourself to. Oh, you made it. Well done. You have to write defuns. It doesn't support the full range of data types and primitive functions and operators. It's still very experimental. We hope to have the first real customer project this summer. If you have something where you really need to do data parallel, because this really focuses on data parallel stuff, please send it to us. Here's a list of the stuff he's been working on in the last year or so. Important things are he now really is compiling to GPUs. He wasn't doing that for the first couple of years. And this business of moving data backwards and forwards, which is a big problem, he's implemented support for declaring that an array should be allocated in GPU memory and stay there, rather than sending stuff backwards and forwards. He sent me a little video around midnight, and I'm going to, apologies to Aaron if you watched this recording.
How's it all going?
I'm only going to show a very, very small piece of this.
Performance features of the Copenhagen compiler and some of.
What? It's 2 a.m. Aaron is watching it. Aaron, I'm sorry, this is going to be very brief. I'm just going to show the best part of it, because we're running a bit late. So around, he shows around 3 minutes, 3:40, I think. Yeah. Oh, that's very gray. Aaron gets to a point in his demo where he shows that he's using GPUs. So he's on a machine which has 2 GPU cards, and I can't remember which one of them we're working on here. He's got this very simple defun up there where he's summing the threes, the elements in a vector which are exactly divisible by either 3 or 5, I think. So 0 equals the 3 residue of alpha, or 0 equals the 5 residue of alpha, compress alpha, and then do the reciprocal, make it all floating point, and sum it. So just to give it some work to do. And The way this works is you can see you have the source for a namespace. So this vector S here is the source for a namespace. In Dyalog APL, he just does a quad fix on that. To run his compiler, he runs co-difference fix. So you take the source of a Dyalog namespace and you run it through Aaron's compiler, and you get a namespace which looks identical. It has the same functions in it. You can call them in exactly the same way, except they run on the GPU. And the numbers that he was able to get on these cards, let's see, is this? No. Then he switched to the other GPU, I think, and he was getting numbers for large arrays. The speed up is going up to a factor of 5 or 6. I think at the end he gets up to about 6, where the timings for the CD co-defens on an array of this size, and there you can see the Dyalog one is 6 times slower. So once you get up enough data moved on to the GPU, you can get some pretty decent speed ups. You know, we'd still like, but you might need higher numbers than this to want to switch to this technology. 6 times might be worth going for. But as I said, this is still in its infancy. I think we've been funding Aaron for about 3 years now, and we're starting to get some really interesting results. So if you have highly data parallel stuff, please talk to us, because the next thing we need is really some worked examples to. Because, you know, one thing is you have a benchmark like this and you can tune it, and of course you can always get good performance when you're aiming at a specific benchmark. You need to test it on general purpose stuff. Okay, so that's one thing we're doing, and that's really aimed, I think, at data parallel rather than task parallel stuff, though Aaron is targeting both. We have a project which is also a compiler, so I'm mentioning it sort of in the same breath as Aaron's work. This is work done by Jay Fode that he's also presented at the last 2 or 3 Dyalog meetings. You can watch his presentations, they're online. What this does is really that it pre-parses your APL function and builds an abstract syntax tree for your APL code. And immediately, if your arrays are small, that removes the large part of the runtime cost of running your APL code. There's this famous experiment by Bob Bernanke again back in, I think in the 80s, on the IP-sharp time-sharing system, where he instrumented the interpreter and measured the average size of an array going through a primitive. And I think it was around 1.5 elements, the average size. Because that includes empty arrays and stuff like that. So a lot of code will speed up significantly if you use this. It's really worth looking at whether this will help you. But in the longer term, once we have this abstract syntax tree for the APL function, we can start applying much more sophisticated optimizations. The kind of things that Aaron has in his compiler become much easier to do when you have this syntax tree, and you can start looking at it and you can recognize, oh, for example, this part of the tree computes a constant. And that actually went into one, I can't remember which release of Dyalog APL. So if you compute something which uses simple mathematical functions or just concatenates strings together and so on, then at fixed time we'll say, oh, that's a constant. And we'll store the constant value with the function. So for some code, that gives a massive speed up, because there are a lot of people who have code that goes something, comma gets, 10 lines of concatenating stuff together. That disappears completely. So that becomes like 100% speed up with this technology. And then, of course, you can do the loop fusion, and you can have where people write, they have x plus 1 appears on line 3, 7, 9, and 11. Once you have the syntax tree, you can say, well, that's x plus 1. X isn't changed anywhere in between. So we'll compute it once and then just refer to it, which means that you can write clearer code, because it may actually be mathematically clearer to say x plus 1 on line 3, 7, and 9, rather than say x1 gets x plus 1, and then etc. So the compiler version is also completely going to even this playing field where, you know, people will tell you, oh, DFUNs are faster than TradFUNs, and trains are even a little bit faster. But once this stuff is fully in production, it's going to recognize that this DFUN and this TradFUN and this train are actually exactly the same thing, and they will run at the same speed. We'll recognize idioms even if you don't write them. There are already some idioms that this compiler will now recognize, even if you don't use the exact spelling for them. So here's a bit of history on what Jay has been able to do. It's 3 releases this has been there. It started with just very simple DFUNs. We added TradFUNs, control structures, references to global functions and variables. And now Jay is the last man standing, still working on stuff for the APL version 15 almost, adding some more goodies for that.
Red dots.
Sorry? Red dots in the editor. Right, so that's something that might not make it into version 15, but that's going to be a feature you can enable, and then when you're writing a function, there'll be a little red dot that says this is not currently compilable, and you'll be able to click on it, and it will tell you that on line 7 there's something it can't compile. So then you can tweak it until it turns gold, or I don't know what color. Yeah, this is to make you guys happy. Better support for nested DFUNs to make Paul happy. Paul Mansour. Well, any Paul. We want to make everyone called Paul happy. People called Paul are surprisingly important to us. It's interesting. Right. Okay. I think I'm not going to demonstrate this. Jay has done some really good talks. The one last year is good. Go and look that up if you want to see it in action. It's 400 IBeam and the name of a function. Just show you this. I think this is public knowledge, Steve, that we're using a benchmark from SimCorp Dimension version 5.5. And this table just shows you how the code coverage has grown. So this is just in terms of the number of functions that we can compile, I think. So that doesn't actually mean it's 83.3% of the CPU time that we're covering. We can compile, we think, about now. In version 15, we're adding another 20%. And Jay's made this table which shows how the addition of each one of these features increased the ability of the compiler to do the work. So the big one here is indexed assignment. That's 20%, another 20% of code that we can compile in version 15. Okay, futures and isolates. So that's really something which is aiming at task parallelism, and it's a mechanism where really the control is in your hands. We'll have a workshop this afternoon where I'll try and go into that in more detail. Very briefly, the goal of this was that if you had asynchronous or concurrent tasks that would consume, we set ourselves a goal of at least 1/10 of a second. So if you had snippets of code that would take 1/10 of a second, you wanted to provide a mechanism that would allow you to fork those off and run them efficiently without losing time to overhead or not noticeable. Aaron also has this idea of futures and isolates built into the co-defense system, and I don't think he's implemented any of that yet, but his plan is that you'll be able to go down to the very, very finest grain of parallelism in his compiler. Because he's a compiler, he'll do data analysis and he'll allow you to use futures and isolates to synchronize real data parallel computations as well, but that's probably some years in the future. So very, very briefly, an isolate is just a Dyalog namespace where if you dot into it and execute something, that runs in a separate process rather than running in a pseudo thread or in the same thread as the main interpreter. We'll look at that this afternoon. If you want to build your own infrastructure that's asynchronous, and we've had a number of projects recently where we've done that. So we built TriAPL, which is you've probably seen that. People can run APL expressions online. We do that by sandboxing every expression and running it in a separate process so that it can't crash the web server. At worst, if everything goes wrong, it will terminate some process. The Dyalog File Server and the futures and isolates mechanisms themselves are all built on the same infrastructure that we're also making public. So you can use that, even if you can't shoehorn your application into futures and isolates, you can have these tools to play with. And let's see, do I have time for a quick demo of that? When do I have?
At least 20 minutes.
I have at least 20 minutes. Yeah, well, let's risk it. Font okay?
Yes.
High enough as well? So there's a workspace here where I've let's see, so I've collected these, the APL process class, which is the thing that allows you to control a remote process. The RPC server class, which is something you can run inside a server process to do work for you. And then there's some code in the workspace that starts the slave process. And as you can see, the comment is it's mostly stolen from our isolate code, which is written in APL by Phil Last and myself. And what it has is just it checks the environment to see whether there's a command line that says you should run as a slave. And then it checks which IP protocol you want to use and stuff like that. And then it has a trap and a message box so that if this thing were to fail while you're debugging it, either pops it up with a message box or it uses quad SM if you're on a character mode thing. And then it boots the RPC server. So it has an example of how to use this with error trapping and so on. And then there's a test function, which I will trace. So we're going to run with development slave so that we can debug them easily. Set runtime to 1 if you want to use runtimes. Initialize conga, and then I'm now going to start 3 slaves on different ports. And I'm going to, so the arguments to the APL process class constructor are the workspace ID, command line parameters, and the runtime flag. So that creates a new instance of a process. I connect to it with conga. I record the name of the connection. I do another one. I do another one. And then I just ask a random client to call the foo function. And that's not very interesting because it just returns its argument. But it's just so that you have a worked example of firing this thing up and putting how to insert your code into it.
So that's platform independent?
It is platform independent. As far as we know, we now do nearly all of our work at Dyalog on both Mac. We have somebody using a Mac, somebody using Linux, somebody using Windows. In the core development team, there's on the C programmer side, there's a majority of Linux users. The C coders prefer Linux. The APL tools group who builds the APL infrastructure tries to use all 3. We can see that Linux is growing, is going to become very, very important. I mean, the announcements from Microsoft in the last 2-3 weeks, they put Microsoft SQL Server on Linux 2 or 3 weeks ago. At Build yesterday, they announced a full bash command shell interpreter as part of Windows 10. Something very, very fundamental is happening, Microsoft and their attitude to open source and Linux. They're clearly deciding that they can't maintain Windows as the primary operating environment for the next decade, or they will lose if they try to do that. So they're trying to, the way Microsoft makes most of its money, I think, is still on the tools, Office, SQL Server, and they need to make that available everywhere if they want to survive. Part of the reason for that is that energy costs are what drive a lot of choices in cloud computing. And the memory and CPU footprint of a Linux machine running a service is very significantly smaller than a Windows machine. Although Microsoft has done all kinds of things to produce what they call headless Windows servers, throwing gigabytes of stuff out. The Linux kernels, especially with this new, what is it called? There's a new form of very ultra-light virtualization supported on Windows. What was it? Jason mentioned it again last week. Anyway, so Linux is ahead on the cloud stuff, and I think that's really driving a lot of stuff. At the very lowest level, all of this stuff is built on Conga, which provides asynchronous communication mechanism between APL processes, or indeed the other side. Sorry? What? Dockers? Dockers, yeah. Apparently they're coming for Windows as well, but you can see that kind of technology is coming out of Linux. And had a major customer ask me last week whether Dyalog was planning support for headless Windows. We are. Don't have a date yet. But of course, if you can rewrite your APL system to run on headless Windows, it can probably run on Linux as well. Right? And we're trying to add features to make everything portable. So we're adding file functions to list the contents of a folder and make directories and stuff like that in version 15, which are all cross-platform and so on. But everything will what? Speak up. Everything will probably be based on Conga. Maybe Conga will learn how to do other things than TCP someday, Björn? Maybe. But that's, and it now allows you to do secure communication if you want to. You have mechanisms for authenticating who's at the other side of a connection, either using certificates or using integrated Windows authentication, and so on. That's the base for most of our work, at least until further notice. As I said, we're just starting to work with a client who has an actual project who wants to do Monte Carlo simulations of catastrophes for an insurance simulation application. And they are planning to run everything on Dyalog APL, on Linux, on elastic compute clouds, and the customer using this will have a drop-down which will say, how many dollars do you want to spend for this simulation on buying more virtual machines from Amazon, and then it will just spin them up. So we'll be working with them to make a toolkit or steal whatever they produce. They're really happy to work with us and open source that level, because that's not their IP. And of course, I don't know how many of you have noticed, in Atlanta, Georgia, there's a provider, aplcloud.com, whose webpage looks like this. I think they are mostly reselling Amazon services, but they focus on APL, so they'll set up a virtual machine for you with APL on it. They'll help you get started. So they're worth looking at, talking to. Right, so right at the tail end, I thought I'd talk a little bit more about some examples of asynchronous things that we have actually done. So these are recent applications we built. TryAPL, we've talked about. Dyalog File Server is a client server version of the Dyalog component file system. And we now have clients actually running into internal audits, either their own or client internal audits, saying those component files, you're sharing them on a LAN, and then you can just switch to the DFS. So it's designed to be a plug-compatible replacement for the Dyalog component file system. And it actually uses Dyalog component files under the covers, so you can roll back and forth. You don't get a new file format by using it. It's just that you can move all the component files to a location which is not on a share that everybody has access to. And then you can use them as before, and in a lot of situations they run faster because the server exclusively ties all the files and manages queues, holds, locks, etc. much better. And then there's the vector database. I'll get to that in a minute. We talked about that. The architecture diagram for TryAPL is you've got a user with a browser, talks to my server. This is unreadable. But there's a master process, but then if he types says 2 + 2 here, we run an asynchronous process using this APL process RPC server framework so that anything that happens in there can be isolated rather than running it. So here it's not really about performance as much about security, isolating what's going on there. The DFS File Server, so here you've got APL clients. That's running a very large number of processes. So you partition your file system up into folders, and you can start, or you can have, in fact, other rules for selecting subsets than folders. You can have computations on the file names. So you can run any number of file servers to serve pieces of your file system. And then there's a server that just handles locks and holds and provides a serial queue. You know, if you have large numbers of users on a file system on shared files, there's no queue, right? So you try and hold the file, you try and hold the second file. If either of those operations fail, you give up, wait a random amount of time, and you try again. And as you go to dozens and hundreds of users, that process the performance of that is very bad when you scale. Whereas here you just get into a queue and you just move down the queue, and when it's your turn, you get the whole. So that if you have multiple users on a file system, this is like, you know, the IP sharp file system, the share file system that you could buy on the mainframe for APL 2. Yeah, version 2. There's also a backup server. The vector database is an interesting project that is also for this guy doing the insurance calculations. So he simulates, I think he wants to simulate like 10,000 years of catastrophe data. And then he wants to look at, you know, what are the worst year, how did the worst year look? Or what's the average of what happened in the 10% of the worst years and stuff like that. And he needed a storage mechanism. And we actually working with him to create one. It's a project, it's open source. It's like KDB or JDB in its fundamental architecture. It just maps APL arrays, one column to one file. And it's very, very fast. It uses the key operator to compute sums. And it's open source. So please look at it and tell us what it needs, or just fix it. Or send a pull request. We sometimes accept them. Okay, so VecDB is very, very small at the moment. I think I have the folder here. This is the whole shooting match. There's really just one dialog file, vecdb.dialog, which is 37 kilobytes. This is a feature of version 15 here, by the way, that we register a file viewer for dialog files. And it gives you the syntax coloring and everything. It just displays that there. And in fact, it works for workspaces as well. It'll show you a tree structure. It's actually, I mean, it's running a dialog runtime interpreter underneath, of course. But it's using the Windows hooks. Even in an email, if you get a workspace in an email, you can read it without having to open the attachment. We had to introduce a special mode so that executable code doesn't actually get executed. Otherwise, it would be a bit dangerous. But anyway, VecDB is this very, very small thing. It's on GitHub. No, I won't show you that. There's, of course, it's test-driven development. So when I add a new feature, I always write a test. And this is large test. I'm not actually going to use that now. I'm going to run a demo. We've already SourceTree. So our preferred tool these days in the Dyalog development group is this thing called SourceTree, which unfortunately, actually it handles APL code very, very well, but it has a bug in its Unicode encoding detection. And APL code fools it because APL code has a very large quantity of ordinary ASCII letters. And then a lot of APL code just has occasional APL symbols, surprisingly few APL symbols. And the UTF-8, so this is just, it's just showing the UTF-8 here. But it handles Git and various other source code management systems. So I just edit stuff in that folder, and then I use SourceTree. And there are a number of other similar Git GUI applications that are all very good. But anyway, let me show you. So here's how much is that? Here's 1 million dates, 100 trades per day. Here's a security key, random numbers between 1 and 10, 1 million of those. Oops, I lost something there. Here's the price, and so I've got, I've got 1 million, 3 million element vectors, and there's the first 5 elements of each one. I'm going to name them. I'm going to say the types are 2-byte integer, 1-byte integer, and float. I can choose, currently I can choose from these type names. We'll probably extend that. We don't have a date type, for example, at the moment. I'm just encoding the dates here as small integers. I have some options. So the block size basically says when we fill a block, how much more space do we reserve in the file. And then I'm going to give it a folder name, and then I say make a new vector database with this name, this folder, these columns, these types, these options, and this data. I don't have to insert the data, but if I already have it, I can just do that. And you see that didn't take very much time, did it? 1 million record insert. What it's done is it's created, I can't increase the font size here easily, but I've got 3 columns. 1.vector, 2.vector, the CC, the size here, 2-byte integer, 1-byte integer, float. They're just Ravel order. The data is just there in Ravel order, and then there's a counter, record counter, and some other metadata. And then I can say, do me a query where the date is 1, the key is 1, and get me the date, the key, and the price. And let's see, do that twice. You see, this is how long it took, 5 milliseconds to search 1 million records and on 2 key values and get that data back. We've got these 9 records back matching that. I can do some, so for all million records, so the where clause is empty. Give me the sum price group by key. How long did that take? Not very long. I mean, this memory map vectors like that is just blindingly fast because it's all in memory. And then, of course, I have an SSD. And then I'm tired of that database straight away. It's gone. One of the things that is really, I think, cool about this and relates it also to the concurrency is I can set options. I can say I want to shard the database. I'm going to split the records into different shards. Shard, I think, is just an English word that means a piece. Usually when you've broken something, right? Splinter, yeah. And so I want to do the sharding on column number 1. I could select any number of columns to be the input for the sharding. And then the sharding function is round up, take the first sharding column. There's only one, so the first sharded column, I would get a vector here of values for a record and divide it by 5,000. So I have date values between 1 and 10,000. I divide them by 5,000 and round up. So basically my historical data, more than 5,000 days ago is going to be in one shard, and my more recent data is going to be in another shard. And then I can say where I want the shard folders to go, right? So here I'm just saying, well, put them on my hard drive, shard 1 and shard 2, but those could be on different file servers, right? Typically, you'll want to run the process that deals with a shard with its data locally if you want high performance. So you would then shard it on 2 different servers and then run shard handling processes that only have local data. So now I can create the database again. I've just added these sharding options, and I can do the same query and get the same results, but in my demo DB now has shard 1 and shard 2, and each one is about half the size of what it was before. But the query function, of course, knows about the shards. Now, of course, the next thing that we have to do, which we haven't done yet, is to create a server that's going to distribute queries to the shards. That's in the pipeline for next week. The first step we have done is that you can open a vector DB and say this folder, and then you can list the shards that you want to open. So this is opening that database only looking at shard 1, and this is only looking at shard 2. So if I now say, well, look for date number 5001 in shard 1, I get nothing. But if I look for it in shard 2, there's the data. So date 5001 is in the later shard. And I close them both. I'll copy the isolate workspace. I'll make 2 isolates. I will do a quad fix of the vecdb source in each isolate. That count there is just to avoid it trying to bring the ref back to me. I don't want that. And then I can say, well, isolate number 1, please open shard number 1. Isolate number 2, please open shard number 2. These could be running on separate machines. And then I can say, isolate 1, isolate 2, dot, and the query ask for date number 1 and date number 6000, and you can see I executed an expression on 2 namespaces, the same expression. The shard number 1 returned the data for the first date, shard number 2 for the second date, and of course my server code is going to do this. Right, it's going to do the comma bar reduce of the results of its queries. So when I say I can do this in a week, I'm pretty sure I can wrap that up nicely in a week. There's a bit more to it, right? But this is still very, very primitive stage of technology. It's basically being developed with this guy in San Jose who has this real need. But if you think you might have a need for that, bombard us with requests. We have our own timeline where we will do things like build this server. We're planning to revise that old ODBC server project that we had 2 or 3 years ago, so we can put ODBC, JDBC, etc. Other standard. I'm sure Progress Software have enhanced their middleware technology since then. So we'll be able to provide all the modern database APIs on top of this, so you can use actual SQL to query it, if that helps you integrate. But your APL system will have this lightning fast routes into the data. Right, erase it. It's gone. Oops, and it's time to wrap up. Yes, now this wasn't on the list of things that Dyalog is doing, but this, of course, is something that John Scholes started, 20, 25 years ago, where he'd gone off and read a book about functional programming, and dyadic systems humored him by allowing him to run this pet project, which I think is actually now completely crucial to the future of APL. We can see the kids who come and do the programming competition, they all go straight for defense because in their eyes it makes APL fully modern, functional array language. It's cool, it's nice, and people who are working on concurrency pretty much concur that functional programming is where you want to go, because the point about functional programming is you give it arguments. You give a function arguments, it uses only those arguments. It doesn't need to lock data that it's sharing with something else. It doesn't need to hold semaphores. You can analyze it automatically. A compiler or even an interpreter that's a little bit clever can look at some code and parallelize it automatically. And even you can read the code and see, oh yeah, you know, it could be run asynchronously because it doesn't have any side effects. So if there's one thing to take away from this presentation, it's in all the work that you do in the future certainly on the computational part of your application. You don't have to use defense, because we will try and make our compilers and so on recognize a function of defense as a functional piece of code just as well as a defense. But of course, it's much easier for people like Aaron who are trying to be really smart to deal with defense, because they know they don't have to do that additional piece of analysis. They know it's a function. So everywhere you can, try and do your database queries, get the data into memory, and then have a functional computation. Don't write loops that go and ask Oracle for the price in the middle of the loop, because then you can't take advantage of a lot of this. Aaron's stuff, when it's running on the GPU, it cannot do ODBC database queries on the GPU, right? It's just not going to happen. And if it did, it would mean that you had ended up with an application which didn't run faster when it ran on the GPU. Maybe it actually ran slower. So there's the list, and I've used 5 minutes less than I had allocated. So I don't know if we have time for questions, or Steve, you can come and hook up. Let's take some questions. Steven.
Years ago, I realized that I wasn't smart enough to reuse variable names. So since then, I've made a practice only of assigning a variable once. So
Right.
the code's only one
Yeah.
definition. One of the challenges of compiling APL, of course, is not knowing even the name class of a token in advance.
Yeah.
And I'm wondering if, in my world, that's nothing which I make use of. And I'm wondering if sacrificing formula is something which would bind something.
Yeah, I mean, all the people who are working on compiler-like technologies agree that it would be nice at some point to introduce optional type declarations into APL, so that you could declare types. I mean, in this building, they've done presentations, and they've built their own type checker. Their presentations at Dyalog user meetings on that. That's seen as an aid to correctness. But of course, a compiler can take advantage of it and make the code run much faster as well. And check errors. You'll get an error if you declare a variable to be float and you assign a character to it. So yeah, that is coming, for sure. And maybe size, rank and size limits, and any hint you can give to the compiler, because when the compiler is trying to decide, well, is it worth running this on the GPU? Well, if it's a 100 million element vector, it might be worth it. If it's an empty vector, don't spend half a second firing up the GPU for it to do nothing. And the nature of APL, good APL code, is type, rank, shape, rank invariant. So it makes the compiler writers, it really puts them in a bad place for writing optimizations.
I was only offering not to use the name again.
Sorry?
I was only offering not to use the name again.
Oh, yeah, but I think in a defun, if you do use the same name again, the interpreter actually fiddles it so that those are different names. It doesn't reuse the names once you're in a defun. Yeah, I've seen your hand. What a lot of the other programming languages do is this JIT compilation technique, right? So they compile at runtime. So they try and collect statistics. Well, it seems X is always a large vector. Or they'll compile multiple versions of the code and pull them out of a hat depending on the size when you come around the next time. So we haven't compiled this one, so we'll just we'll do another compilation for this, for rank 2, and use that. And Jay Fode, who's now the CTO of Dyalog, I am the CXO, I don't know if you noticed that. The ex-CTO. He has a background in writing compilers and so on, so he's really, he wants to do all these things. Yeah. Sava.
We have some experience with GPUs in the past.
Yeah.
Something in our experience is that, for example, one example reported one saver volatility model from number computing to GPU. Acceleration was quite good, but they didn't like the delay to set up, for example. Also, one of the problems from time to time was the amount of data, because of the limited space on that stuff.
Yeah.
So this something like you say, okay, 6 gigabytes is enough, but very often that's not enough.
Yeah. And
we also did some experiments with port indexing to GPU, the database indexing. In some cases, okay, that was something just initial, but our conclusion was at that moment, that several years ago, maybe searching was good enough, worth accelerating, but not everything. So we need to talk about GPU, yes, but a lot of things can be done, but you have to be very...
Yeah, but as I think I had on one of the early slides, is it's all, it's application specific. You can't just write something and say, now we'll run on the GPU and your application will be 25 times faster. Well, no. Sometimes, maybe, yes. Yep.
We've got comments from Aaron, if you'd like to speak up.
Hey, Aaron, are you really there? What time is it? It's
Yeah, it's a fun hour, but yeah. I wanted to mention.
I hope I didn't wreck your presentation too much. I did get it a little bit late.
Yeah, no, I think you did just fine with the time constraints I gave you. I wanted to mention that in the static type declarations things, the CodeDefense compiler already does static type inference on code to avoid any runtime overheads related to the element level data types in arrays, and that's already implemented in the CodeDefense compiler. And the next step is to do that same type inference for rank and shape specializations. And in the future, there are plans to do static type declarations, but that's quite a ways away.
Yeah. It's a large field. And writing compilers that are faster than APL interpreters that have been optimized for 50 years is quite a challenge. Yeah.
Yes.
Yeah, I think one of the things you did in last year, right, was add support for Boolean arrays to the compiler, because that's sort of the first place where the compiler writer fails, is you think you can write faster C code than the APL interpreter can do. But if the APL interpreter is using 32 times less memory for its computations on current machines where the memory access is so becoming more and more important, the fact that APL has, and Dyalog APL in particular, with the 1 byte and 2 byte integers, the fact that we have very compact data representations actually is becoming a major asset as we move to clouds and so on. But it makes life hell for the compiler writers.
Yes, that was disruptive, the Boolean vectors.
So thank you for doing all that hard work. Yeah. Oh, Paul? Last question.
Just quickly, VecDB, obviously might be of interest to us. But just quickly, what's your thoughts with sharding if a data append comes along? Would you consider the append to be a new shard or appending to each of the existing shards?
No, we look at each rate. We apply the shard fin to the key column for the data that's being appended, and then we direct it to the individual shards.
basically open to your shard definition, so you can decide how you want to.
At the moment, we're only doing the, I can't remember if it's vertical or horizontal, but it depends on your point of view, right? You can split the records into different shards. You might also want to split the columns into different shards. Databases, you know, can often do both. Are you? Where do you want to be? I should press the button.
I will make Steve next presenter.
Get out of here.
Oh, okay.